This is section 14.4, arc length of curves. Arc length was covered in Calculus 2 classes, but it mainly had to do with arc length of curves that were given as regular old real-valued functions. In Calc 3, we're mostly dealing with more complicated kinds of functions, vector-valued functions, where you input a number, like a parameter time, and you get out a vector in either the plane, like you get a 2 vector, or you get a space vector out with 3 components. We still want to be able to find arc length using this. If you remember arc length from Calc 2, it generally led to a bunch of disastrous integrals, but some of them were pretty nice and some of them were interesting puzzles. So that's what we're heading for here, is like, how do we find arc length now that our curves in space are given mostly by vector-valued functions? First thing is we want to remember how this worked in Calculus 2. I guess some people maybe had it in Calculus 1. Anyway, I'm going to give the super summarized version here because I don't want to redo too much of Calc 2, but essentially the super summarized version is, say you have a curve. If you zoomed in on a little piece of the curve, as long as the curve is differentiable, if you zoom in on a piece of the curve, it looks like a straight line. That's the point of Calculus 1, really, is that any smooth curve, when you zoom in on it, it basically looks like a line. That line is the tangent line. So the super summarized version of how to find arc length is you say, well, if you want to find arc length, you should try to find a little bit of the arc length. Let me get some other color here. You should try to find a little bit of the arc length called ds. And then after you find a little bit of arc length ds, you can integrate ds to get s, which is the arc length. Well, how do you deal with a line segment that may not be, that's not perfectly horizontal or vertical? You draw a right triangle. That is an ugly right triangle. Let's do a little better. It goes over by a little bit of x and up by a little bit of y. So all of our derivations boiled down essentially to this plan, which is that you can use the Pythagorean theorem on this little tiny triangle. And then the plan would be that you can find s by integrating ds. Now, you can't actually do an integral when the ds is in this form, so you need to write it in some other way. We had 2 ways to do it in Calculus 2. One way was to do everything with respect to x. So you'd have dx squared and dy dx squared. This is the same thing as what I had in the previous step, except I've got too much dx in the denominator. You can think of this as factoring out dx from the square root. This isn't... Well, let's just finish this and then talk a little bit about whether this is a legitimate argument. dx is 1. dy dx has a name that's the derivative of y. So you would usually write something like, oh, well, I'll take the derivative of your function here. And then your final value of the arc length would be, well, to find s, you should add up all the little pieces of s. And so your formula would be that you integrated the square root of 1 plus f prime of x squared. Now, a possible complaint about this is, come on, the core thing that makes this work is the mean value theorem, and you didn't use the mean value theorem here. I would argue that you should have access to a couple different kinds of proofs. One should be the kind that you can remember so that you can reconstruct the formula from scratch if you need to, and that would be this. You should worry if you invent this off the top of your head that like this doesn't feel like it was okay, but as long as you know that there is another proof one level deeper that guarantees that this works, then you're okay. So I'm going to show you this kind because we don't have time to redo all of Calc 2. The other formula you may have gotten in your Calculus 2 class if you did some parametric equations was to do the whole thing dt, so you factor a dt out of the right side. So instead of dx dx and dy dx, now you'll have dx dt and dy dt. Now the integral is all in terms of t, and so this would be the formula you would use if you had two parametric equations defining your curve. Again, s is add up all the little bits of s, and here is one way to write all the little bits of s. I guess I would write this as x prime of t squared plus maybe y prime of t squared. The sheet of notes here expects me to go and do the mean value theorem argument, but I'm not going to. Anyway, you have you can find the arc length of a curve given by a function of x using the left-hand formula. You can find the length of a curve that's given by two parametric equations using the right side of the formula, and the two parametric equations is the one closer to what we have in Calc 3. In Calc 3, we're talking about vector-valued functions, where you hand the vector-valued function a parameter, t, time, and it gives you back a vector, maybe in the plane, maybe in space. And the vector will have like two components. So we'll end up having an answer, like our formula in Calculus 3. This will be the right kind of formula over here, the parametric one. The final formula is the same, of course. You get s by adding up all the little bits of s, which means you add up all the... okay, so if it's y equals f of x, then you get 1 plus f prime of x squared dx. Yeah. And then if you have everything in terms of parametric equations, you have a formula for x and a formula for y, then you'll get that s is the integral of ds, which is, well, there's just another form of ds, which is x prime of t. Here x is given by f of t. And y prime of t. Here y is given by g of t. And then you get to do your integral with respect to time. So for a two-dimensional vector-valued function, a vector-valued function that's in the plane, you can use this formula to find the arc length s. Now, the question might be, okay, great, what do we do if we have a three-dimensional vector-valued function? But the trick is that, like this Pythagorean theorem plan from chapter 13, we know it just keeps working, even in higher dimensions. So you don't actually need to like remake everything. All of the same ideas still work in more dimensions. So you'll get to say that s is still the integral of ds, and you'll get a similar formula, except now you'll need to include x, y, and z. The integral is still with respect to t. Now, there's a little issue here, which is that if you take all the components of a vector, square them all, add them up, and take the square root, that's the magnitude of the vector. So we can actually simplify these formulas a little bit. Here, we've taken the x component, the y component, and the z component of r prime, and we've squared them, added them up, and taken the square root. So we've taken the magnitude of r prime, and that's what we're actually integrating. Now, this simplification, this isn't total nonsense, like this isn't like a coincidence. What does the absolute value, what does the magnitude of the derivative mean here? Well, the magnitude of the derivative is the speed. So this once we're finally done, like simplifying everything down to where it's easy to look at, what we're saying is that the distance you travel when you go on a curve is the integral of your speed, which is a physics 1 or a calc 1 idea. Again, the distance traveled is the integral of the speed dt. Let's make sure the units work out. Speed you might think of as being measured in meters per second, and then time, dt, is measured in seconds. So yeah, you end up with meters, which is something you would think of as a distance. Okay, let's see how to use this in practice. To find the arc length of a helix, we've seen some helices. Helices are circles that are going up in the z. They're circles in the xy plane or in some plane, and they're going up or down in the z plane. So here, this one in x and y is a circle that's spinning around at triple speed, and then it's going up at 1 unit per time. Well, how do you find the arc length? Well, you find the arc length, you find anything by integrating all the little pieces of the thing. Then you look up what ds is, and the easiest one to remember is that a little bit of distance is found by taking the speed and multiplying it by a little bit of time. So we're really getting all the way back to distance is rate times time here, like way back in math. It's just that this object, which we've been learning how to deal with in all of chapter 14, this object is the complicated object that you have to be okay with dealing with. So first we'll find r prime of t. I'll have to drop r prime of t in here. But the derivative of a vector-valued function you get by taking the derivatives of all the components. So I'll have minus 3 sine 3t, 3 cosine 3t, and 1. Now that our integral is a t integral, I can drop some bounds on it. The bounds here are from 0 to 2 pi. Because those are t bounds, I can just put them on the integral. It wouldn't make sense to put 0 to 2 pi here on the s integral, because that would imply that 0 and 2 pi are values of s, but I've got them here on the t integral. Okay, now I can just read what this says. This says the magnitude of this vector. So I'll find the magnitude of this vector. To find the magnitude of a vector, you take the square root, you square all the components and add them together. Let's leave a little more space. So square the first component, 9 sine squared 3t. Square the second component, 9 cosine squared 3t. And square the third component. This maybe looks like it's lucky, but it's not really lucky. Circles do this a lot. Anyway, sine squared 3t plus cosine squared 3t is 1. So when I factor out the 9, I get 9 times 1. So in total, I'm integrating the square root of 10. Well, I can factor out the square root of 10. Now, what does the square root of 10 mean here? The square root of 10 is the speed that we are traversing this curve. Remember, the magnitude of the derivative of a vector-valued function is the speed of the curve, if you think of the vector-valued function as like a path that a particle is following. So what we found here is that even though this looks like a complicated path, the path is actually moving at a constant speed of square root of 10. Well, if you move at square root of 10 meters per second and you go for 2 pi seconds, you get 2 pi times the square root of 10 as your distance. Yep. On to the next page. On the next page, we'll see one where it doesn't go quite so well. It's basically just not perfect trig identities saving the day. But if you want to find the arc length of a curve, you say, well, the arc S is the arc length, so I'll find S by adding up all the little pieces of S. And then I can look up the appropriate form for ds for the situation. And here the easiest form for a little bit of distance is the speed times a little bit of time. It's now a t integral, so I can look up the t bounds, and the t bounds are from 0 to 2. Okay, now what is the speed? Well, the speed is first take the derivative of the vector valued function and then find its magnitude. I'm not going to do too much at once. I'll start by finding r prime of t and drop it in here. The derivative of 2 with respect to t is 0. The derivative of t is 1, and the derivative of t squared is 2t. This vector is the velocity vector, and when we take its magnitude, we get the speed. So let's take its magnitude. The magnitude of this is the square root of the sum of the squares of the components. So I'll have 0 squared plus 1 squared plus 2t squared. Cool. What's the plan with this integral? So if your plan is a substitution, the substitution should be what your first plan is. Unfortunately, a substitution is not going to work here, because if I let u equal the inside function, I need some kind of t's on the outside to deal with the derivative of the substitution. So that's not going to work. If I go into... So I'm going to have to do a trig substitution to get rid of this squared. Luckily the 1's already here, so... I'll try to write this as 1 plus something squared, so that I can figure out what trig function to use. 1 plus tangent squared is secant squared, so I'll let 2t equal tangent theta. Then I can take the derivative. 2 dt is secant squared theta d theta. I don't have a 2 dt, so I'll solve for dt. It's half secant squared theta d theta. Further, I've got some t bounds, so let's turn them into theta bounds. If t is 0, then tangent theta equals 0. Tangent theta equals 0 when theta is 0. If t is 2, then tangent theta equals 4. So theta is arctan of 4. Gross. Okay, so the integral is from 0 to arctan of 4 of the square root of 1 plus tangent squared theta times dt, which was half secant squared theta d theta. At this point, we have the square root of 1 plus tangent squared theta, which is the payoff of a trig substitution. This is all secant theta. So in total, I have secant cubed theta. Secant cubed theta is some kind of ridiculous curse, and it seems to be mostly reserved for arc length problems. I don't know why this happens. It seems like unnecessary, like it's some payment that we have to make for something horrible that the human race did in the past. I'm not doing the integral of secant cubed theta. So we're going to ask a computer to do this for us, or you can look it up in a table. But basically, at this point, nothing particularly good is going to happen with the answer, and I'm just going to get a numerical approximation of the answer. So let's get can I get this projected? Some Wolfram alpha, maybe. A little bit. So I'll do the integral from 0 to arctan of 4 of 1/2 secant cubed theta d theta. Does it know what I'm talking about here? It does. So I end up with root 17 plus a quarter of the arc hyperbolic sine of 4. Nice, whatever. Okay, in this situation, so in most situations I would prefer that we see an exact answer, because the exact answer it contains more information than an approximation. This 4.65 that I'm going to write as the final answer is an approximation. However, in the case where the exact answer is essentially impossible to read, we kind of lose a lot of the benefit of writing the exact answer. So in this case, I'm going to write 4.65. I shouldn't write that it equals 4.65. Let's say that it's approximately 4.65, and I'll say that I used Wolfram alpha. I guess if I'm using Wolfram alpha at the end, there's an argument that I should have just used Wolfram alpha at the beginning. That's kind of unfortunate. I guess the point is that most integrals you will end up being able to just do them. And you'll be able to get actual quality answers. But in this case, we didn't get anything nice. So 4.65 it is. Okay. We're going to use something called an arc length parametrization later. Now, the reason that we want to do this is there are a lot of different parametrizations of a given curve. If you have a circle, you can go around the circle at one speed, or you can go around the circle at a different speed. And those are different parametrizations of the same curve. So let's see it in Desmos, actually, before we go on. Just the idea that there's multiple parametrizations of the same curve. So you could have cosine, we'll use A, sine A. Let's go only forward and go from 0 to 2 pi. This is a parametrization of the unit circle. Now, there are other ways to parametrize the unit circle. If you instead use cosine of 3a, sine of 3a, you trace out the exact same curve, but you trace it out in a different amount of time. It's a different parametrization of the same curve. Similarly, you can parametrize the same curve using like minus cosine of 4a minus sine of 4a. Or you could even like switch the sine and the cosine. Oh, you need one of each. All of these are different parametrizations of the same curve. The different parametrizations are going at different speeds, and the different speeds is the key thing. Is like, is there a parametrization that would be better, that would have like the best speed, that would make our life a little bit easier? That's the question here. And the answer is yes. The answer is that the best parametrization is to use the parameter arc length. Now, this is going to get awkward, but let's see. So the arc length function, we already have an arc length function, which is that s of t is this integral of ds. So it's the integral of r prime of the integral of the speed. And the best, so we're looking for a parametrization that's the best one. And essentially the easiest way to do that is to pick a speed. If we use the parametrization where our parameter is s, so instead of like using time as our parameter, we actually make sure to like lock in our parametrization to the arc length, then we'll make sure that we are tracing out the curve at a speed of 1. And later in this chapter, that will make our life a lot easier. So, yeah, so we'll later try to use the parameter s in our parametrizations instead of like all the different kinds of parametrizations that go at different speeds. In the end, we will end up saying that the simplest form of of the arc length formula is we'll integrate ds over the curve c, and this will help us talk about line integrals later. I can't get too much into the details this section, I don't think anyway. I think it's mostly in the next section. But the takeaway here is there's lots of different parametrizations of any given curve, and the parameter doesn't have to be t. Maybe there's some way for us to use s as our parameter. I've skipped this sentence here. That's okay. Okay, on to the next page. So we'll get back to arc length parameterization in the next section. But essentially, we're just going to use the formula for the arc length that we got in this section when we do that. Okay, last thing we want to do is look at a helix. So the arc length of a helix is kind of like a circle, except we've stretched it out so that it's not contained in a plane. Part of it is like it's gotten stretched out. So it's going to be a little bit longer. And the question is, if you take a circle with radius r and you stretch it out into a helix, does it get longer? And if so, like how much longer? So this would be a fun discussion topic if we were in a standard face-to-face class, but you should try to imagine like if you have a circle, or above it you have like part of a helix that just goes one time around a circle. Is that more wire, or is that like more string if you build it out, if you physically built it? But we can just calculate it. So let's compute this arc length. We should be pretty happy with the arc length being the integral of the little bits of arc length. And I kind of want to start writing this c here, that I'll say this is the integral over the curve of all the little bits of arc length. So instead of writing bounds, because I don't know the bounds of the arc length, like I don't know like 3 to 4 or something for s. Instead, I just know I want to follow this curve, this one. And usually we name curves c, just because it's c for curve. It's not c for circumference. We usually name curves c, and then I write it here. So it's just something to start to get used to as we approach chapter 15. Anyway, the way we actually calculate it is we find the speed and multiply by a little bit of time. Once we're in a time integral, then we can use the bounds for time. Here the bounds are from 0 to 2 pi. So let's do it. The speed is, let's first take the derivative of r. I can take the derivative of each component. So I'll get minus r sine t, r cosine t, 1. Then I need the magnitude of this vector. Remember that vector is the velocity vector. And once I take the magnitude, now it's the speed, which isn't a vector anymore. So I'll square all the components, add them together, and take the square root. Scroll this down a little bit. Then we notice, as usual, that when we're dealing with circles or helices, something good happens. Namely, if I factor out the r squared, I'll get 1. So I'll have r squared times 1 plus 1 dt. And at this point, I again have the square root of a quadratic that I have to integrate. The last time this happened, we saw what happened. We were like, oh, I want to do a substitution, but I can't do a substitution, and so I'll have to do a trig substitution, and then it was a total disaster. This one is not a disaster. You should look at this and try to figure out why not. Why we don't need a substitution at all. The reason is, there's no t's in here. This is a constant. Factor the whole thing out. The square root of r squared plus 1 is a constant. It's not changing with time. It doesn't depend on t at all. And this integral is 2 pi. So my final answer is that the arc length of this helix is 2 pi square root r squared plus 1. We should notice, since this was the point of the question, was, is this more or less than the circumference of the circle we started with? Well, 2 pi r can be rewritten this way, 2 pi square root of r squared. So in fact, the length of the helix is a little bit longer, because the square root is a little bit larger than the square root over here. So rs is a little bit more than the circumference. Just to recap, this c that's in this integral stands for curve. It stands for the helix. And this c here stands for circumference. And that's just because there aren't enough letters to talk about everything we want to talk about in math. So you have to start to get it from context. A c under an integral, like as the bounds of the integral, represents an object, where a c in an equation represents a number. But overall, I want to save you from just watch to make sure that your integral is actually hard before you do something difficult. This one was not difficult. I think that should do it. Is there one more? Oh, how does this relate to 2 pi r? Yep. So it's a little bit bigger than 2 pi r. So that's section 14.4, arc length.